So the final apportionment method we will explore is the Huntington-Hill method. It is the preferred method used today for apportioning congressional seats. It utilizes determining a standard divisor and a standard quota just like in the previous examples, except the standard quota is then compared to what is called a geometric mean. And the formula for the geometric mean is m times n, and then we take the square root of that. So the square root of m times n. Now, when we come up with our standard quotas using the quota rule, m is the lower bound and n is the upper bound. So this example states, suppose 19 new school buses need to be allocated to 4 high schools within a school district. Using the Huntington-Hill method of apportionment, determine how many buses should be assigned to each high school according to the enrollments shown in the table. So here's our table here. These are our separate subgroups, these different high schools. These are the enrollments for each high school with an overriding total here of 1,755. So the first thing we'll go ahead and do is we'll determine the standard divisor. So we'll take our total population here and divide it by the number of seats or the number of items. And of course, that's the 19 new school buses here. So we'll take 1,755 and we'll divide that by 19. So our standard divisor is approximately 92.368. So the next thing we do is we determine our standard quotas. So we'll divide our standard divisor into each one of the subgroups here. 458, if we divide that by the standard divisor of 92.368, and that comes out to be 4.958. And 3 decimals here will be plenty. The next subgroup, divide this by the standard divisor. 547 divided by 92.368, and that's 5.922. The next subgroup, divide by our standard divisor, and this is around 2.717. And then for our last subgroup here, 499 divided by our standard divisor of 92.368, and that's 5.402. So then we determine our geometric mean, and we do that by taking the lower bound and the upper bound once we use the quota rule. So the lower bound for 4.958 for this standard quota is 4. The upper bound is 5. This is our m. This is our n. 4 times 5, that's 20. We then take the square root of 20. The square root of 20 is around 4.472. And again, 3 decimals is plenty. For our standard quota here, the lower bound is 5. The upper bound is 6. We multiply the 2 together. 5 times 6 is 30. The square root of 30, and that's around 5.477. And we do that for each subgroup. Our lower bound here would be 2. The upper bound would be 3. 2 times 3 is 6. The square root of 6 is 2.449. And for our final subgroup here, our lower bound again is 5. Our upper bound is 6. 5 times 6 is 30. The square root of 30, and that's 5.477. Now the next step is we compare the standard quota for each subgroup to its geometric mean. If the standard quota is less than its geometric mean, then we round the standard quota down to the next integer. If the standard quota is greater than its geometric mean, then we round the standard quota up to the next integer. So obviously here 4.958 is greater than 4.472, so we round the standard quota up to 5. The standard quota here, 5.922, is greater than its geometric mean of 5.477, so we round the standard quota up to 6. 2.717, the standard quota here is 2.717. Its geometric mean is 2.449. The standard quota is greater than its geometric mean, so we round this up to 3. And the standard quota here, 5.402, is less than 5.477, so we round the standard quota down to 5. 5 and 6 is 11, plus 3 more, that's 14, plus 5, that's 19. So all 19 of the buses were allotted according to their apportionment here. Now, if it doesn't come out to be 19, if we have a leftover, or if we have too many or too few, then we would have to determine a modified divisor rather than using 92.368. Depending upon if this is greater or lower, we'd have to modify this and then use the modified divisor to come up with a modified quota. And then we go through the process again of a lower bound and upper bound and coming up with a geometric mean. But for here, it worked out okay. And that's it.